Hello and welcome to the AI Research Roundup. I am Alex, your host. Today is May 12th, 2025. Alright, so today we are looking at a research paper from Hugging Face's trending list, published just about 11 days ago, titled R&B, Domain Regrouping and Data Mixture Balancing for Efficient Foundation Model Training. This paper introduces R&B, which stands for Regroup and Balance, a framework to better mix data for training foundation models. It first regroups data by semantic similarity, meaning how alike data is conceptually, then balances these groups using a Graham matrix. This matrix is a tool using domain gradients, which track learning changes per data group to optimize the data mix. Okay, so this first figure really helps visualize the regroup part of the regroup and balance framework. On the left, it shows taking broad data categories, like open question answering, and repartitioning them into finer-grained clusters based on semantic similarity. This often uses embedding similarity, which is a way to mathematically represent data to see how alike items are conceptually. Then, the middle graph shows that training with these new, specific clusters leads to a lower loss, meaning the model makes fewer errors compared to the original broad categories. The rightmost graph, for the DALI 15K dataset, further shows there is an optimal number of these clusters for best performance. Following on from that idea of optimal clusters, this next set of graphs really drives home the point. The top row shows that across different datasets, like DALI 15K and SuperNatInst, there is indeed a sweet spot for the number of regroup domains, minimizing evaluation loss. The bottom row then introduces the silhouette score. This score, which measures how distinct and well-separated data clusters are, often correlates with lower loss, as indicated by the R-squared values. This correlation suggests we might predict data mixing performance based on how good the clustering is. Okay, this table then really quantifies the benefits, especially the computational efficiency. It compares the regroup and balance framework against several other data mixing methods like stratified sampling, which is a common baseline, across 3 datasets. We see columns for the model's loss. Lower is better here, and the percentage of computational overhead. This overhead, essentially the extra computing power needed for the mixing strategy, is dramatically lower for regroup and balance, often less than 0.1%. And crucially, this efficiency comes while still matching or even beating the loss scores of other, more costly methods. Alright, so this next figure really drives home that performance aspect. The table on the left highlights how regrouping data before applying different mixing strategies consistently improves outcomes. That is, it lowers the loss. You can see the underlying values show where regrouping beats the original data grouping, and the regroup and balance framework, when combined with regrouping, often achieves the best overall performance, as shown by the highlighted cells. Then, the graph on the right vividly illustrates training on the SuperNatInst dataset, showing the regroup and balance framework, labeled R&B, achieving a lower evaluation loss and doing so more quickly than other approaches. Building on that point about quicker convergence, this table provides a more formal look at the computational cost. It compares different data mixing methods, showing their total compute cost in flops, which are floating point operations per second, a measure of computational work, and, critically, their relative compute overhead compared to standard training. The regroup and balance framework has a remarkably simple overhead term here. This simplicity is especially beneficial when the number of skills or domains, denoted M, is much smaller than the volume of evaluation tokens or training tokens, leading to that dramatically lower computational cost we discussed earlier. So moving beyond just the cost, this figure visualizes the balance part of the regroup and balance framework in action. We are looking at the evolution of domain weights, which represent how much influence each data category is given over training steps. It is really interesting how the framework intelligently changes this emphasis. For instance, Domain 1 and Domain 5 clearly get much higher weights as training progresses, while others are downweighted. This adaptive process, using readily available training information, is central to its strong performance with such low overhead. Okay, so this adaptive balancing, using readily available training information from tools like a Graham matrix, which is a mathematical way to capture relationships between data domains using their training gradients, is really at the heart of why the Regroup and Balance framework, or R&B, is so effective. This framework, a two-stage method for foundation models, which are those large AI models trained on broad data. First regroups data by semantic similarity, that is, by how alike data points are in meaning, and then balances their influence. The main takeaway is that R&B achieves excellent performance with incredibly low computational overhead. Thanks for tuning in to the AI Research Roundup.